Dear physics aspirants, right now I have the center of mass, and the center of mass subtopic will come from system of particles and rotational motion. When you study the physics +2 level, you will get center of mass. We shall first see what the center of mass of a system particle is, then discuss its significance. For simplicity, we shall start with two particle system. We shall take the line joining the two particle to be the x-axis. You will see here. Let us distance of the two particles x1 and x2 respectively from the same origin O. Let m1 and m2 be respectively the massage of the two particles. The center of mass of the system, that point C, which is at C, which is distance x from O, where x is given by x is equal to m1 x1 plus m2 x2 by m1 plus m2 7.1. In equation 7.1, x can be regarded as the mass weighted mean of x1 and x2 if the two particles have the same mass. m1 is equal to m2 is equal to m, then x is equal to mx1 plus mx2 by 2m is equal to mx1 plus is equal to x1 plus x2 by 2. Thus, for two particles of equal mass, the center of mass lies exactly midway between them. If we have n particle of masses m1 and m2 mn respectively along a straight line taken as the x-axis, when by definition of position of the center of mass of the system of particles is given by, here you will see here, this formula will be applicable, and where x1 and x2 are the distance of the particle from x origin, x is also measured from the same origin, and the symbol sigma, the Greek letter sigma, denotes summation, in this case over n particles. The summation m1 is equal to m is the total mass of the system. Suppose that we have three particles not lying in a straight line. We may define x and y axis in plane which the particles lie in, represent the positions of the three particles by coordinates x1 y1 x2 y2 and x3 y3 respectively. Let the masses of the three particles m1 and m2 and m3 respectively. The center of mass C of the system of three particles is defined as the located by the coordinate xy given by x is equal to u naught y, and for the particle of the same masses m1 and m2 is equal to m and is equal to m3, and you will see here 3m. Now you will solve and you will get y is equal to, you will see here, thus the three particles of the equal mass, the center of mass coincides with the centroid of the triangle formed by the particles. Result of equation 7373b are generalized easily to a system of n particles not necessarily lying in a plane but distributed in space. The center of mass in such system is xyz, where the summation you will see x, y and z. Here m is equal to summation sigma. Summation m1 is the total mass of the system. The index I runs from 1 to n. m1 is the mass of the, here you will see nth particle of the position of nth particle of the given by xy and x1 y and z1 equation. You will see here and can combine into the one equation using the notation of position vectors. Let r1 is the vectors and positive vectors of the nth particle, and r to be the positive vector of the center of mass. You will see here the adding of vectors. R is equal to, you will see, and r is the vector, and summation m1 r1 is vector. Sum the total right hand side is the vector sum. Note the economy of expression we achieve by use of vectors if the origin of the frame of reference, the coordinate system, is chosen by b, the center of mass. Then summation m1 r1 is equal to 0 for the given system of particles. A rigid body such as a mass streaks for flywheels is a system of closely packed particles. Equations are therefore applicable to a rigid body. The number of particle, all atom or molecules in such a body is so long that it is impossible to carry out summation over individual particles in these equations, since the spacing of the particles is small, and we can treat body as a continuous distribution of mass, and we subdivide by the body into the n small elements of mass, as you will see m1, m2, and mn, and the nth element of m1, m l as ith mi is taken to be located about the point x y z to 1 and the coordinates of the center mass are the approximately given by summation x is equal to summation, and as we make a bigger and bigger and each smaller, these expressions become exact. In the case we denote the sums over I by integrals, thus you will see here calculus can be used. Here m is the total mass of the body and the coordinates of the center. You will see here the coordinate of the center of the mass now x, and here you will see calculus x dm same kind y you will see, and z5 and the equation 7.5a. The vector expression equivalent to these three scalar expressions is here. You will see if we choose the center of mass as the origin of our coordinate system, r is equal to 0 and r is vector, o is vector, and you will see calculus xdm, you will see here 7.6, and often we have calculated the center of mass of homogeneous bodies of regular shapes like rings, discs, spheres, rods, etc. By homogeneous body, we means a body with uniformly distributed mass. By using symmetry consideration, we can easily show that the center of mass of these bodies lie in their geometric center. You will see here the determining of cm of a thin rod at x-axis. Now here you will see let us consider the rod whose width and breadth in case the cross section of the rod is rectangular, or radius in case of the cross section of the rod is cylindrical, is much smaller than its length, and taking origin of to be the geometric center of the rod and x-axis to be along with the length of the rod, we can say that on account of reflection symmetry for every element dm of the rod at x, where there is an element in the same as dm located at m located minus x figure 7.8, and net contribution of every such pair of the integral, and hence the integral xdm itself to 0, and equation 7.6, the point of for which the integral itself is 0 is the center of mass. Thus the center of mass of a homogeneous thin rod coincides with the geometric center. This can be understood on the basis of reflection symmetry. The same symmetry argument will apply to homogeneous rings, discs, spheres, or even thick rod, circular or rectangular cross section for all such. But as you will realize that every element dm at a point x, y, z, one can always take an element of same mass at the point minus x minus y minus z. In other words, the origin of a point of reflection symmetry for these bodies. As a result, the integral in equation 75 all 0, and this means that for all the above bodies, their center of mass coincide with the geometric center. Here you will see here the sum numericals, and you will see here an answer is here. You will see with the help of this picture you can understand what I am going to want, what I am going to say to you. We will meet in the next discussion with many more leftovers of the physics +2 level. Till then, thank you.